Hello and welcome to 123 AP Physics with Zach Speaks a Science Geek. This week we're going to be covering impulse momentum. So what is impulse? It's the product of a force times the duration. So work was the product of the force times the distance in the x direction. Well, this is the force times the time that the force occurs for. And it's equivalent to the change in the momentum of an object, which can be calculated by taking the mass of the object and multiplying it by the velocity. There's two units for impulse. You can say Newton times seconds, so Newton seconds, or kilogram meters per second. They are the same unit. There are just different ways of writing it. I typically use Newton seconds, but with momentum, there's an important thing to know, and it's gonna be pretty important specifically with collisions, which is one of the main uses of momentum, is working with collisions. So the center of mass of a system is a mass times the displacement of the origin. And you do that for every single mass in the system. You add them all up and you divide by the number of masses in the system. It's like a weighted average. And to find the velocity, you just take the displacement and take that out and put the velocity instead. So it would be the mass times the velocity. And then you plus however many masses times their velocities. And then divide by the number of masses in the system. And the reason this is important is because in collisions, the velocity of the center of mass of a system is going to be the same before and after the collision. And that's something that's useful to know, and we use that. It's what part of the conservation of momentum. So what can we use momentum for? We can find the change in an object's motion for an impulse, or find the impulse needed to produce a certain change in the object's motion. But the most important thing we can do with it is work with collisions. And so there's three types of collisions. There's the perfectly elastic collision, where both momentum and kinetic energy are conserved. There's the perfectly inelastic collision, where the objects stick together after the collision, but kinetic energy is not conserved, but momentum is. And there's a perfectly inelastic collision, where the objects do not stick together. Momentum is conserved, but kinetic energy is not conserved. It's sort of in between the two. And so one of the nice shortcuts with the perfectly elastic and perfectly inelastic collisions is if the sum of the momentum of the system. So say there's a 2 kilogram object traveling at 3 meters per second and a 3 kilogram object traveling at 2 meters per second in the opposite direction. If you added those two momentums up, because momentum is a vector, so it has direction and it has a negative sign, the sum of the momentums would be 0. And so if it was a perfectly elastic collision, the two objects would hit, and then they rebound with the exact same magnitude of velocity, but the opposite direction that they were originally traveling in. And if it was a perfectly inelastic collision, the two objects would hit and they just stay motionless. And so that's a nice little shortcut. It doesn't happen all that often, but when it does, it makes solving the problem a lot simpler. Okay, so we're going to start working on problems, because the only way to really teach this is work through problems. There's not a whole lot of theory behind it, it's just a lot of practicality. And so a 0.75 kilogram baseball is thrown by a pro baseball pitcher is initially traveling at 50 meters per second. That's like 100 miles per hour. Another player hits the baseball and causes it to begin traveling at 30 meters per second in the opposite direction. So big change in speed. So what is the impulse provided by the player hitting a ball? So we would use that the impulse is equal to the change in momentum. So it's the final momentum minus the initial momentum. So it's 0.75 times by 30 minus 0.75 times by negative 50. And you add that up and you get 60 Newton seconds. So the impulse was 60 Newton seconds. The next problem. A 200 kilogram rocket engine is capable of producing 200,000 Newton seconds of thrust. If it is attached to a spaceship in outer space with mass 25,000 kilograms, what will the final increase in the rocket's speed be? So here we'd set the impulse equal to the change in momentum once again. So we'd say that 200,000 Newton seconds is equal to 25,000 kilograms plus the 200 kilograms that the engine weighs times the velocity, and it's just solving a linear equation from there. And so the velocity is about 7.9 meters per second. So it's not really traveling that fast. It's about 16 miles per hour. It's not really that fast because that spaceship is very heavy. But if they use 3 or 4, it'd start going pretty fast. Okay, next problem. A 2 kilogram block traveling at 6 meters per second collides with a 3 kilogram ball traveling at 4 meters per second in the opposite direction. The collision is perfectly elastic. What are the final speeds of both objects after the collision? So this is one of those examples about the sum of the momentums of the two objects equaling 0. So this problem, you can immediately find the answer. The 2 kilogram block is going to travel at negative 6 meters per second, and the 3 kilogram ball is going to travel at negative 4 meters per second. It's going to travel at 4 rather, because it's initially traveling in the negative direction. So negative 6 and 4 for the two. But I want to teach you how to do it without that shortcut because it's not always going to happen. So what you do is first you set the initial and final momentums equal to each other. You say that 2 kilograms times by 6 meters per second plus 3 kilograms times by negative 4 meters per second is equal to 2 kilograms times by V1 plus 3 kilograms times by V2. And so looking at this, there's two unknowns, so we need another equation. So we'd say that 1/2, we'd do the same thing for the kinetic energy. So we'd say that because the collision is perfectly elastic, we can set the final and initial kinetic energies equal to each other, and that will give us our second equation, and then we just solve as a system of equations. So we can say that 1/2 times by 2 kilograms times by 6 meters per second squared plus 1/2 times by 3 kilograms times by 4 meters per second squared is equal to 1/2 times by 2 kilograms times by V1 squared plus 1/2 times by 3 kilograms times by V2 squared. And so we'd solve as a system of equations. I'm not going to show that. It's you guys all know how to solve as a system of equations. And so you would get that V1 is negative 6 meters per second and V2 is 4 meters per second. And just as I said in the beginning, so this proves that the shortcut works, but it also shows how to solve it if the shortcut isn't usable. Okay, problem number 4. A 7 kilogram block traveling at 6 meters per second hits a 4 kilogram block traveling at rest. The 4 kilogram block then begins traveling at 9 meters per second. What is the speed of the other block? So here we know that the blocks do not stick together. It doesn't state that it's a perfectly elastic collision, so we don't want to assume that. But momentum is always conserved in every collision. So we can set the initial and final momentums equal, and we'd say that 7 kilograms times by 6 meters per second plus 4 kilograms times by 0 meters per second is equal to 7 kilograms times by V plus 4 kilograms times by 9 meters per second. And solving for what V is, we would get that V is 0.86 meters per second. So there you go. That's how you'd solve a partially inelastic collision. Problem 5. Okay, the objects stick together. That's the first thing that jumps out at me. So this is a perfectly inelastic collision. So we know that the objects are going to stick together after the collision. So that there's only going to be one final speed after the collision, and the mass is going to be the two masses added together. So a 10 kilogram block traveling at 12 meters per second collides with a 3 kilogram block traveling at 7 meters per second in the opposite direction. The objects stick together after the collision. What is the velocity of the blocks after the collision? So we'd say that 10 kilograms times by 12 meters per second plus 3 kilograms times by negative 7 meters per second is equal to 13 kilograms. I'm sorry, that should be kilograms right there instead of meters per second times by V. solving for what v is, we would get that it's 7.6 meters per second. So there you go. That's how you solve a perfectly inelastic collision. And I think it's time for the FRQ. Yes. So pause the video, start working through it. I'm going to read it out and then start working through it myself as usual. An object of mass 3 kilograms initially traveling at 23 meters per second in the positive x direction method. It's another object with mass 9 kilograms. After the collision, the 9 kilogram object begins traveling in an unknown angle, positive x, positive y, and the smaller object begins traveling in the negative y direction at a speed of 10 meters per second. Find the x and y components of the momenta for each object. Find the speed of the larger object. And find the kinetic energy of the system before and after the collision, and use this information to determine what type of collision this was. Okay, so the first thing I'm going to do here is I'm going to create a table with all the values. So calculating from the initial, we can say that 3 kilograms times 23 meters per second is 69 newton seconds. So that's the total in the x direction, and there's nothing in the y direction for the total. Then we look at the object that bounced off the 3 kilogram object, and we say that 3 kilograms times 10 meters per second in the negative y, so that's negative 30 newton seconds in the y direction, and 0 newton seconds in the x direction. So from this, we immediately know that object 1 in the x direction has 69 newton seconds, and in the y direction has 30 newton seconds. So from that, we can calculate the magnitude of the velocity, because it's a vector, so we just use Pythagorean theorem, and that'd tell us the magnitude of the velocity, which is what that problem asked for. Find the speed. But if you wanted to find the angle too, like your teacher asked for that, you'd solve it as the system of equations, or you could do tan inverse y over x, and that should get you the same thing. Hold on, I'll put in my calculator right now. It's 30 over 69. Yeah, it gets you the same thing, 23.5 degrees. So it gets you the same thing. You can treat it as a system of equations, solve it that way, or you can treat it as vectors, and it's a lot simpler that way. Okay, so the other part of the problem was find the kinetic energy of the system before and after the collision. Use this information to determine what type of collision this was. So, pretty simple. This is an energy thing. So you just say that 1/2 times by 3 kilograms times by 23 meters per second. And then that thing squared is equal to 793.5 joules after 1/2 times by 9 times by 8.36 meters per second plus 1/2 squared plus 1/2 times by 3 kilograms times by 10 meters per second squared is equal to 464.5 joules. Alright, so we can immediately rule out perfectly elastic collision. The objects didn't stick together, so it would be a partially inelastic collision. That's all for this week. Next week is going to be a long video. We're doing circles, because with circles, there's basically an analog for everything we've learned. Kinematics, rotational kinematics. Dynamics, rotational dynamics. Energy, momentum, everything. There's an analog. So tune in next week, watch the video. It's going to be a long one, but it'll be very interesting, very educational. See you next week.